The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
The discussion today is about planning for the control of construction tolerances and deflections. So as a quick introduction, contractors want to build fast and safe and efficiently with the least amount of remedial work as possible. That goes without saying. But unfortunately, what's stacked up against us is a disconnect between Division 3 and Divisions 8 and 9 of the project specifications. Division 3 being the concrete and 8 and 9 being various finishes. Engineers designing buildings that are increasingly more efficient, slender, thinner, and lightly reinforced, and more highly stressed and more susceptible to deflection and creep. And there's, of course, higher expectations of the design team and owners for dimensional tolerance, which speakers this morning also highlighted. Just some thoughts, like in pre-construction, one of the things we're thinking about when we're looking at a job is obviously what the definition of the project tolerance is. And our typical yardstick of what we wish to deliver is defined in ACI 117. And then we're discussing with our owner and our design colleagues discussions about anticipated slab deflection, slab shortening, and column shortening. And then we like to bring up very early in the whole process potential conflicts between the structure and the cladding. In particular, the window wall systems, and it's needed to accommodate long-term deflections, but also not mentioned there is like slab shortening. And of course, the flooring. We typically scrub the project drawings and specifications to ensure that we're looking for conflicts and definitions, and then also formed face finish requirements. This table here you've already seen a couple times. It's from ACI 318. This is the old the 2014 version, so it's table 9.5. But it defines deflection limitations. Typically, you get L over 360. And then below there is an excerpt from one of the flooring specifications, and in particular, they talk about that 1/8 inch and 10-foot rule. And that's what the flooring contractor as well as the owner might have as an expectation. We at the beginning of the project like to point these conflicts out and manage and shape expectations. Some slab deflection problems that we are challenged with. Excessive deflections that exceed ACI 318, Chapter 9 and or Division 9 can result in some really costly remedial measures, such as placing latex-modified concrete leveling, modifications and or repairs to exterior cladding, repair of damage to interior partitions and finishes, replacement of poorly performing floor finishes, such as hardwood flooring, and again, windows, alignment of doors and hallways, kitchen cabinets and countertops, of course, back pitching of balconies, elevator door frames, and window head and sill trim highlight deflections. What I mean by that is you have a particular window trim, and it's true and plumb, and where the slab edge may not line up with that, or like you might have a trim piece that is level, and you might have deflection, which again you have two lines that should be parallel, and there might be that your eye is drawn to that. Here's a photograph of a slab deflection problem. This is a back pitch on a balcony. Again, when we placed the concrete and took our measurements after the slab was cast, the top of slab elevation was within all project tolerances, and the pitch was there. Unfortunately, because of the span, the back span, and also because of post-tensioning, it caused basically erasure of that initially cast-in slope. So we basically ended up creating a pond. Another issue that we're constantly challenged with is slab shortening problems, such as with cladding, window wall, and brick. There's the issues of aesthetics of exposed concrete at the walls and columns where plumb windows meet leaning columns and walls, and window frames highlight slab shortening issues. Here's a picture of a embed connection for the window, And basically, there's a lot of stuff going on here. This is where the sharp and pointy end of construction, concrete construction tolerances meet the tolerance requirements of the cladding system. And I don't know if you can see there, but you see the two bolts, and they're in the slotted connection that's going in the left-right. And you would think that the anchor bolt should be like in the center of that slot, but we've already gobbled up all our tolerance right out of the gate. So this worked, but just. And the issue here was most likely due to slab shortening due to the post-tension forces acting on the slab and causing that whole slab edge to move inwards. Again, as the previous speaker in the morning session stated, it's very common to see it come in 3/4 of an inch or 1 inch. Here's another example of a slab shortening problem. This is, again, the window system conflicting with the slab edge. There's a balcony here. This is towards the far corner of the building, and the whole slab is basically shortening to the right. And because of that shortening, we've bumped into our window cladding system. So we've had to go back and do some remedial measures and saw cut around there. Again, we're trying to anticipate these things, but we still bump into them, and we're again being more and more proactive now, trying to get a handle on what slab shortening may be, and then communicate that to our cladding partners. And here's another example of slab shortening issues. This is a photo of of a soffit or underside of a slab, and then you have a window system, and you've got that window head piece. And the slab has shortened to the right. And the cap piece there was sized to accommodate a certain amount of slab edge tolerance, but it unfortunately did not include the slab shortening. So we're left with this ugly result, which we had to resolve. But again, this slab shortening is actually quite a common problem. Column shortening problems, that's also an issue, and particularly in taller buildings. We typically are on the lookout for issues with column shortening on towers above 40 stories in particular. And we usually end up with issues with window systems, alignment of doors and hallways, again, kitchen cabinets and countertops, elevator door frames, and distress sometimes at connection between column walls and spandrels. The differential shortening, there's restraint at these spandrels, and you sometimes have cracking. And this is a photo of it. This is at a connection of an upturned beam and a column, and there was some differential column shortening, and there was a rotation there, and we ended up having a spall, which we had to go back and repair. So some thoughts on what a contractor's perspective are. What we want is we want to build fast. Typically in the Chicago market, we're targeting a 3-day pour cycle, and we like to plan the work to proceed safely on a fast, efficient schedule, and to deliver the project to meet all the project specifications, divisions 3, 8, and 9, as said previously. And of course, get paid. So we're trying to plan ahead to avoid costly remedial work or disagreements about noncompliance. And as previous speaker in the morning stated, we can be on the hook for quite a long time. In the state of Illinois, the statute of repose is 10 years. That's really a long time. So being asked about where your concrete was poured and where top of slab or edge of slab and stuff like that, and be able to have to defend yourself and potentially be on the hook for remedial actions, it's a problem. What the contractor can do to influence or improve slab deflection performance and tolerance, of course, is the selection of the formwork system. Construction equipment, such as the tower crane, concrete pump, and placement booms, where they are. And so, for instance, with the tower crane, the example would be an inside climbing tower crane where we're no longer supported off of a foundation and we're relying on shoring and reshoring to support the tower crane weight. There's some massive forces, and the design of that reshoring is critical. Of course, then you have the mixed design, hot weather, cold weather construction methodologies, in particular, ensuring that curing agent, something as simple as having your curing agent applied. That really plays into shrinkage. Location of pour breaks and construction joints, the rate of construction, and the QA/QC program, making sure that we're, putting the concrete where we're supposed to, and also putting the rebar where we're supposed to, and then ensuring that we have the proper curing conditions. So, like I said previously, our estimating team, we need to price in tolerance issues, contract clarifications to identify tolerance conflicts, and attempt to allocate responsibilities appropriately. And really what that means is managing client expectations. Coordinate tolerances with other trades. So like I said previously, like again, understanding what our Division 3, our concrete deliverables can be, and pointing out that cladding and finishes need to have realistic expectations and need to design, have their systems designed to accommodate deflection and tolerances. Discussions of anticipated slab deflections, slab edge shortening and column shortening, lateral building, and deflection story drift with the engineer record. We really need their input, and they need to provide us information in addition to just what's on the construction documents. So that means slab deflection contour maps, as well as actual written estimates provided to us for slab edge shortening and column shortening and story drift and whatnot. So again, we can communicate that to other people who are going to have to interface with our cast-in-place concrete structure. And then review of the construction means and methods, schedule and budget with regards to project tolerances and deflection. And so this is the tool we use. This is our patented McHugh RFI launcher. And there's a team of McHugh estimators, construction managers, and basically launching questions to our partners, both on the design team side as well as our subcontractors with the finishes. And so again, the key to success is communication. One of the things that we do to improve our ability to more accurately place our concrete where we're supposed to is we've pretty much moved to a 3D BIM model for our layout. So on the left is the old way with the 2D AutoCAD with the various points that the tech engineers would use to lay out. And now we're developing 3D BIM models, not only for the initial estimating, but we're doing it for actual layout and construction. And to achieve better coordinated layouts as well as more accurate placement of concrete. And we're big fans of the Tekla products and Trimble systems, and so we basically are using the Tekla environment to model our building, and then bringing that into the field with a total station. And just a few words about field layout. Our benchmark, we're always bringing it in from the outside of the building, and we're continuing to do that throughout the whole project. Of course, the building is moving as we go up, and so like a benchmark where you had initially brought up, it's changing because obviously the building is moving, it's shortening, and so it's changing, so it has to be continuously updated. For buildings less than 20 stories, we typically like to provide targets around surrounding buildings and take shots off them and coordinate those to bring our control lines. For buildings over 20 stories, building sway actually becomes too big of an issue. And so we like to bring up using a bomb site, which that basically means you've got a hole and you're basically taking like it's looking down at a point below, and then bringing that point up every seven floors, and then check back to the outside. So basically keep on closing the loop and ensuring that we are where we think we are. And there's a constant issue and a challenge with conflicting control lines between concrete and other trades. Our rule is like everyone uses the concrete's control lines except for the window cladding company. Because they're bringing up their own thing and where they're shooting for, and so they're basically shooting for true and plumb. But all the interior finishes are using our control lines. And then we have our monitoring program. What we're trying to monitor as we construct is formed surface finish quality, slab deflection, slab FF, and FL, but really doesn't, as stated multiple times previously, FL is not really appropriate for supported slabs after the shores are released, and especially not appropriate for cambered slabs. And monitoring column shortening. Our slab monitoring program, we're measuring the top of the slab versus the bottom of the slab, so we're measuring the formwork before we cast, and then measuring the top of the slab after we cast. And then the number of the shots and location. We have a document that we create where we set all our control or points. We're going to take data. We share that with the design team so they know what we're recording and when we're recording before we start this. We measure the top of formwork prior to concrete placement, top of slab immediately after concrete placement, but prior to PT stressing. We go back and take shots again after PT stressing and the release of the shores. And then after all the shoring and reshoring are removed, that's typically about 30 days, Ideally, we would like to go back again a second and a third time if the schedule allows us, and if it's a particularly like a slab that we're concerned about in terms of performance. But typically, with our market, our interior finishes are close behind us, so we don't typically have the opportunity to take 90-day topless slab elevations. We also take a perimeter bottom of slab to validate window wall rough opening at the moment we're casting, and then edge of slab to identify potential curtain wall issues. Things that are of debate is the accuracy of the survey data, whose control lines, and then tolerance of the slab thickness, and then what's the purpose of these monitoring programs. Again, straightening that all out beforehand with the design team and the ownership, so they know what we're measuring and they know what to expect and the purpose of this data. And then comparison of the field data to the structural engineers' predicted short-term slab deflection is very much a good thing to do. So if there is an issue, we can make some like adjustments as we continue up the building. So if you're, like said previously, if you're doing like a three-story building, there really isn't much opportunity to do this. But if you're doing a 40 or 50 plus building, we're getting data continuously. We're submitting that to the design team, and we can make adjustments. Here's a case study of a project we did in Chicago some years ago, recently. This is a 50-story high-rise in Chicago. It's 505 feet in height, and it's roughly about 675,000 square feet. The podium is which is levels 1 through 14, is a mix of retail, lobby, parking, and amenity level. And then above that, levels 15 through 50 are residential levels. And the construction period was 18 months. And the typical floor is just your typical mild reinforced concrete slab. It's an 8-inch two-way flat plate, roughly about 10,500 square feet. And the maximum spans for the exterior bays are about 22'7", and the interior bays are around 23'9". And I got the like L over a H, the span to depth ratio, about 33.9 and 35.6. The concrete strength is your typical 5,000 psi, and our rebars are your typical number 4 and 5, grade 60. And the specified cover are 1-inch top and 3/4-inch bottom. And the design loads are typical, residential loading of superimposed dead load of 25 dead and 40 live. If we go to the ACI table in Chapter 9, if you go by those prescriptive methods, you would require a 9-inch slab thickness. So this is a pretty thin slab. And here's just an image of the typical floor plate. You got the core on the right-hand side there, and you have a whole series of columns around the perimeter, which are relatively short spans, about like on the order of like 19 feet. And then you have the north-south, you have the longer spans. And then this is what the engineer record provided to us. They told us like maximum long-term deflection values of approximately 1/2 inch on the interior bays and about just about 0.42 of an inch on the south bay there. And we were like, again, we're being doing our due diligence. We're looking at this, and because it's a reinforced concrete slab and it appeared to be somewhat thin, we thought we should take another look at it. So we commissioned our own, just an internal slab deflection study. We do this quite often, and it's a useful tool to basically get our own feel of what we think the slab's going to do. So using a commercially available software package, we just modeled our slab, and we created our own independent slab deflection analysis. And here's a contour map, and we're getting a bit more deflection. So we're getting approximately 1 inch on the interior bays and about 0.9 of an inch on the south bay. So again, more. As stated earlier by other speakers this morning, this analysis and the engineer records analysis are both correct. There's a lot of variability in deflection design, and so there's a lot of uncertainties with the material. And with tolerance and of bar placement and whatnot that could result in the differences. And also, of course, you've got the nonlinear creep shortening, cracking as well that play into this ambiguity. And also the methodology of the different software packages, whether you have a time-dependent analysis or not. This is our field measurements. So we recorded 84 points on this slab. We took a series of measurements, first the day after placement with the full shoring, and then second measure taken, we took it initially when it was cast, second when we after release to shores, and then a third time after a month after the removal of all the shoring and reshoring. And we were getting a lot of data, and so we could use this to help us understand how the slab was moving. Comparing what we recorded versus what we predicted, we found that the locations of the points of maximum deflection, what we measured and what was predicted by both McHugh as well as the engineer record, were the locations matched, but the differences in the actual magnitude was interesting. So 1 month after the slab was cast, we're getting about 0.48 of an inch at the interior and about 0.52 of an inch at the exterior base. So we've already got the predicted long-term deflection. So, and this is just a comparison, but based on our own analysis before construction, with our independent analysis, we suggested camber and that we installed, and it helped us to control the deflection and get a better performing slab. One of the issues and challenges with camber, in our opinion, is having a camber less than 3/4 of an inch is pretty much useless because it tends to get erased by the finishers. As Eric had mentioned, getting camber, specifying camber and actually finishing the concrete to actually maintain camber does take planning and really good communication with the finishers. They need to know where the camber line is, and obviously choose the appropriate finishing equipment to get it, because it can easily be erased. Here's another challenge that we have, that's a recent development, is bathrooms have large format tile. You're going to get these large tile pieces that really have strict FF requirements. And so one client of ours requested separate FF numbers for bathrooms, even though the minimum sample size is 10 by 10. So they were asking something that was really out of bounds with the rules. And then finishing at the toilet and tub penetrations, our estimators need to carry these costs. Details that potentially vanish within acceptable tolerances. Balcony depressions and window wall interface. Again, you're talking about a 3/4 inch step, and so it has to be lined up, so you get the window wall right there. And so with construction matching all the ACI 117 limits, so we're within the bounds of what that requirement. We could be out of bounds with our window wall balcony. Sloped PT balcony may back pitch over time. So again, you've got this long-term issue in terms of deflection, and with the deflection, you're losing your pitch on your balconies. And then facade features, long-term risk if coverage not within tolerance. Here's an illustration of an architectural detail with could be argued as an unreasonable client expectation. So again, you've got a 3/4 inch pitch, you got a window wall, and you've got basically a 3-day pour cycle, and you got to make this. It's a challenge for us sometimes to achieve. But again, we do this every day, but it doesn't happen by accident. It happens by careful planning, and then obviously communication to the ownership and design team. And then, of course, even with significant pre-construction effort, there still may be surprises. In other words, the window system arrives on site which don't match the shop drawings. We've gone through great effort to understand what our rough opens have to be, and tolerances for, and then the shop drawings are all reviewed, and so I guess what we learned was have inspections of the window manufacturer, because they may show us one thing on the shop drawing and something else arrives on site. So in conclusion, better planning for deflection and tolerance equal less remedial work, cost savings, and a happy repeat client. Buy the same tolerance from all the trades, and communication is the key to success. Thank you.